when it comes to numeric integration, there are typically obvious choices of how to actually calculate the estimate, the approximate integral. So you're interested once again in some integral going from a to b of some function f of x dx, and you want to get it numerically. So if we were to actually draw some function, so let's draw a function looking kind of like this, and let's suppose that this is a and this is b. What you can do in order to estimate the integral is you can subdivide this area, because what we're essentially interested in is this area under the curve from here to roughly here. So in order to get some approximate value, what you can do is you can subdivide. You can say that we're going to subdivide the range from A to B into 4 strips. So I'm going to subdivide it into 4 separate strips like so. Now, in order to be able to estimate the integral, we have to decide how we want to treat these strips. And typically, we want to treat them as rectangles because calculating the area of a rectangle is rather simple, and we don't have to deal with the curvature of the function or anything. Of course, it doesn't give us an exact value, but it gives us a value that's good enough. So under the midpoint rule, the midpoint rule basically says the following: once you made the subdivision, how about we take the midpoint of each of the strips across the x-axis? So we take this point, this point, this point, and this point. And what we do then is we actually evaluate the function at this point. So we grab this point, we look at what the function actually is. So the function will be obviously at this point, and then we treat this strip as a rectangle, which obviously has the width, let's call the width dx, delta x rather. So this is going to be the width of the strip, and the height of the strip is going to be treated as this value, and this value happens to be f at, well, let's call it f at xi, where I is the index of the actual strip center. So essentially, we're taking this rectangle that I'm drawing in white, and we're getting its area. We're getting the area of this. Then we do the same for the next strip. So once again, we take the midpoint, we evaluate the function, which we turn it into a rectangle, and once again evaluate this area, and we continue until we run out of strips. So essentially, the width of each strip, like for example the width of this strip, we can say is delta x times f at xi. Or if we want to actually use the terms for a and b, we can sort of formalize this a bit further, in the sense that we can, for example, say that the estimate of the integral, the approximate integral, is actually a sum. Now remember, each of the strips is delta x wide, so we can put the delta x here. Now by delta x, obviously we mean that given we made a subdivision of n strips, delta x is actually defined as obviously b minus a divided by n, because the overall range is b minus a, and we have n strips here, so it's b minus n divided by a. So then we take the sum, and to sum, we need to calculate the actual values at the midpoints. So that's essentially using our function. So that's going to be a function at a particular point, and we can certainly just call it xi and be done with it. But in actual fact, this midpoint here is a, well, first of all, we start on the left, so it's always a plus, and then if we give it an index, let's say I going from 0 to n minus 1, I'm starting with 0 because I want to have the vanishing part if going from the left. So that's going to be a plus, and then we take as many delta x's as there are indices. So we say I times delta x, and then we also take another half of the range. So we essentially take another delta x over 2, or we could sort of we could group these together if we wanted to. So this formula essentially allows us to estimate the approximate integral based on these midpoints of the strips that we've created. Now let's take a look at how this is done in MATLAB. Okay, so here is the implementation of the midpoint rule in MATLAB. It's actually very simple. So we have a function called midpoint rule, and it takes 4 arguments. The first argument is the function that we're actually integrating. The second 2 arguments are the limits of the integration, and the final argument is the number of strips that we want to subdivide the range into for purposes of estimation of the integral. So first of all, we calculate the delta x. That's just the difference between the integration limits divided by the number of strips that we want to make. And now that we have the width of the particular strip, we calculate the value of the function at this strip. But to do that, we need the actual x coordinates. So to find those x coordinates, the coordinates of the midpoints, what we're essentially doing is we're saying that we're going to start at a point a plus delta x over 2. So that's the first midpoint. And then we go up until the last midpoint. And the number of midpoints is obviously the same as the number of strips. So that's the value of n. So now that we collect the x coordinates of each of the midpoints at which we're evaluating the function, we simply say y equals f of xi, and that gives us essentially a vector of y values, and all we have to do is add up those values together and multiply them by delta x. So let's take a look at how this actually works in practice. So I'm going to call the midpoint rule. We'll take a function like the cosine, and we're going to evaluate it from 0 to, let's say, pi over 2, and I'm going to start with 10 strips. So if I evaluate this, I get 1.001. So this is very close because we know that the actual value is 1 exactly. We've actually overshot the value by just a little bit. So if we increase the number of strips to 100, for example, you'll see that we're getting more precision now. We're getting 1.000, and then we get some error, an error here. And as we keep increasing it to, let's say, 1,000, we're getting even better. So essentially, this basically shows that as you increase the number of strips, then obviously you're getting a more accurate result.